Good morning, good morning, my fellow scientists. It's Wednesday, January 11th, and science is feeling a little bit low. On Monday, I talked about how my light box casts a rainbow when I use a collimated beam. I can only see an image of a rainbow when I use a scattered light source. So I'm going to talk about why that is. Let's talk first about the beam method, where we have a collimated beam of white light that strikes a diffraction grating. Now at this point, you're going to see some of the light pass straight through and some of the light be diffracted. Now the diffracted light, we're going to see the blue light come out, the green, and the red. And if we put a detector right in front of one of these beams, we see that. But in general, what you're going to see is the scattered light from the piece of paper that's below. Right, so from this part of the paper, we're going to see some scattered red light. From this part of the paper, we'll see the scattered green light. From this part of the paper, we'll see the scattered blue light. And of course, from the central column, we'll see the scattered white light when we put our camera in this location. Now, on the other hand, if we set the scattering element in front of the light source, so this is a scattering element, such as a tissue paper, white light is sent out in all directions. At that point, our diffraction grating is going to cast essentially a rainbow from every single point on the diffraction grating itself. So from up here, we're going to get a blue, a green, and a red emitted ray. From here, we're going to get a blue, a green, and a red emitted ray. And also from here, a blue, a green, and a red. And if we put our camera down here, as we did, what are we going to see? We're going to see the appropriate line at the appropriate angle, cast directly from the diffraction grating itself. You'll also notice that the way this is set up, the order gets reversed, because at the steeper angles we see the red, and at the shallower angles we're seeing the blue. This week, Science News reports that a 20-cent paper pinwheel could transform medicine in the developing world. Now that's an aggressive headline, but I love the idea that you can take a few very inexpensive parts, create a high-force centrifuge that's capable of pelleting blood cells from small blood samples. According to this article, the pinwheel-based centrifuge can spin at 100,000 RPM. Pretty impressive for a hand-cranked device. The original article was published by the Prakash Lab out of Stanford University early this year. Centrifuges are really important for doing any kind of biomedical research. They make for cheap, rapid separations of particle suspensions, including blood, but also of other diagnostic elements such as affinity particles, not unlike the ones I am trying to make with my microfluidic device. An inexpensive point-of-care centrifuge that can be used without electricity may well be of use to physicians who are working in environments where equipment and electricity are not reliable. I put a link below in the description. I hope you'll check it out. Tune in next time for more about open source hardware and an update on the particle generation using microfluidic devices.